Hello everyone, I'm Yao Yao. I'm going to talk about our work, Mnemonics training, multi-class incremental learning without forgetting. This is a joint work with Yuqing, An, Bernd, and Qianru. Multi-class incremental learning aims to learn new data by incrementally updating a model trained on previous data. In the first phase, we get the first model using a training set of data 1, and then we evaluate this model on the corresponding test set. We do the similar in the second phase, but we are aware that the original data 1 is not available due to the memory limitation. What we can do is to update the model with second phase data only. We then conduct the evaluation on all concepts the model has learned so far, which is the standard setting. The same applies to the third phase and so on and so forth. It is known that the model is easy to overfit to the new phase data but forget the previous. This problem is called catastrophic forgetting. To tackle this problem, people generally allocate a small memory budget for previous data and replace the model training. In the first phase, before deleting data 1, we sample and store a small subset we call exemplars. In the next phase, we adapt the model using data 2 as well as data 1's exemplar. This enhances the model 1's representation of data 1. The same applies for the third phase and so on and so forth. So the question arises, how to get efficient data exemplars? Existing methods are mostly about herding, that is picking up the nearest feature of mean representation, or simply using a random sampling. They are heuristic and less likely to be optimal. In addition, their selection is always limited to a finite training set. In our work, we propose a new method called Mnemonics training, leveraging a bi-level optimization to generate more superior exemplars. Our training is totally end-to-end, and our generated exemplars are selected in the continuous space of synthetic data. In incremental phase I, we have the exemplars for previous phases and the original data for the current phase. We aim to learn new exemplars to best represent them. That is to say, we want the model trained on the new exemplars as close as possible to the model theta I star, which is trained on the original data for the current phase and the exemplars for previous phases. We propose to formulate this as a bi-level optimization problem as follows. For the global training flow, we alternate the learning of our mnemonics exemplars and the classification models. In incremental phase I, we learn the mnemonics exemplars by solving a log2 bi-level optimization problem. In the figure, we can observe that compared to the state-of-the-art, our method boosts the accuracy significantly, for example, over 10% in the 25th phase. For the results in the table, we are able to say that our method is generic and it can be easily plugged in and boost the different baseline method. In this Disney visualization, each color region is for one class. For each class, deep color points are the exemplars, and the light color ones are the original data here for reference only. We can see that compared to the baseline method herding, our mnemonics exemplars yield a clear separation in the data space. In addition, they are mostly located on the boundaries between different classes, which is essential to derive high-quality classification models. For more details, you can visit the project website. We have released the code on GitHub. Thank you for listening, and we are happy to answer any questions.